do teams from different engineering disciplines successfully collaborate throughout the product's lifecycle when each domain uses different software? This was the subject of a 2019 ProStep Action Group benchmark project. The ProStep team for Cross-Disciplinary Lifecycle Collaboration, or CDLC, invited participants to help define best practices across the areas of processes, roles, data models, and software architecture. The challenge? Today's complex products require closer collaboration across the many engineering domains that help to define, design, and build them. Even though data from each of these domains is created and stored in different siloed engineering software tools, it is nevertheless related. Today's demonstration will show how the Aras platform can create and manage digital links between related data in separate software systems. These relationships allow change and configuration management processes to be driven by the platform out to the separate tools where the data was originally authored, improving collaboration among cross-functional teams. In this example, a series of hardware, software, electronic, and systems engineering changes will be required to boost the vehicle range for a Mars rover model. Information from across engineering domains will then be used to create a single manufacturing process plan in the end, while allowing for variability by manufacturing site. The Aras Innovator platform offers built-in services to connect with data in external systems through a mix of synchronization and federation. This means the platform can store and synchronize data from those external software tools or display a live view into the data as it updates. Both approaches will be used throughout the demonstration. Once the different data elements are available to the Aras platform, users can create and define the relationships between them. This process establishes links between related data across engineering domains, even if that data was authored in very different software tools. These links provide governance over change in the external tools. Let's see how this works. When teams realize a change is needed, they can navigate throughout the product structure to find everything that the change will impact. They then initiate the change process with a single master change object, which launches sub-changes to notify each of the external systems that the change is needed. Finally, the change is implemented in each of the external authoring tools. This demonstrator is architected to work the way a lot of manufacturers work today, with many different engineering software tools spanning both desktop and cloud architectures. For our purposes, additional instances of Aras Innovator on separate cloud technologies will represent those other tools, which could be used by internal teams or external suppliers. This demonstration will start by showing how the system administrator can manage data links between the platform and the external software tools. The systems engineer, working in one of these external tools, a desktop systems modeler called Cameo, will add a new system element with a brand new requirement. You'll see how federation works to bring the new system element and its requirement into the platform. There on the platform, the systems engineer can map parts from software, electrical, and mechanical domains to the system elements and requirements they fulfill. Finally, the software engineer will update the part with a new version of software to support it. Let's begin. The system administrator logs onto the platform to view and manage the external systems that are connected to Aras. Their descriptions and the technologies that were used to connect them are all visible here. Drilling down, they can see the fields that are mapped and the fields that are federated depending on the type of relationship that was selected. Over in one of these external tools, called Cameo Systems Modeler, the systems engineer will start editing the systems model. The systems engineer will add the Raspberry Pi system element plus a new requirement to the test rover. Now, the updates are checked into Aras. Logging into the platform, we can see that the data we just added in Cameo is available here. Here's the new requirement, and here's the Raspberry Pi part. This custom view of the data shows not only the system model, which is linked to Cameo, but also additional parts added in Aras from other external software tools. These are live links, so let's go ahead and look at the test rover model. The graph navigation feature in Aras shows the logical links between related data throughout the system. It's another way to navigate to the new system elements we just added in Cameo. Here, the red and gray boxes represent the Cameo data, and the orange boxes represent data from other engineering domains that were linked here in Aras. Those could be electronic, mechanical, or software parts. They can share requirements, and those relationships are visualized here too. Next, we'll drill down into the new system element we just created in Cameo and see how these links are created by the systems engineer working here in Aras. The platform lets us associate a physical part to the system element, either one that's already visible to the platform or a brand new part we create on the fly. We'll start by adding the mechanical and electrical parts already visible to the platform. Then we'll create a new software part and see how that process works. The temporary part created by the process can alert a software engineer that a new part is needed. But first, let's go see that the requirement we authored back in the systems modeling tool was also automatically brought over into a requirements document. It's number 7 on the list. When the software engineer logs in, he can find the temporary part that the systems engineer just created. Then, he does a live search out to an external ALM tool. Here, he registers the software part he built and stored there in that external tool. This process associates it with the Raspberry Pi system element already in Aras. Now, a relationship between the Raspberry Pi system element and its physical parts, including mechanical, electrical, and software components, is all set up and can be managed by the platform. And that is significant for engineering change. Let's see how. The second half of this demo will show how these critical relationships governed by the system model enable a cross-disciplinary change process. First, the product manager creates a master change request governed by a CM2 process that includes a change coordinator. The PM will begin by associating requirements to the change that relate to the issue that prompted the change in the first place. Next up in the change workflow, the change coordinator will perform the impact analysis. This checks for parts and other items that the change will affect. The change coordinator launches sub-changes to each of the external software tools based on the engineering domain they support. Finally, a series of domain engineers across electrical, mechanical, and software engineering will all receive the sub-changes and update the data in response. Those updates can be pushed back to the platform. Let's take a look. The product manager starts by generating a new master change to increase the range of the rover by 5%. The PM knows this is an issue because he received notification from an external system, in this case, Jira, which he'll attach here to the change. That way, anyone who investigates this change can have visibility back into what kicked off the change in the first place. Before sending this change on to the change coordinator, the product manager will search for the requirements that he knows this change will impact. The 2-hour battery life requirement we just authored in Cameo, and the overall requirements document for the test rover, which it's a part of. He adds both to the master change as he goes. Next, the product manager advances the change to the change coordinator, who receives the workflow task and begins to review the change. Here, the change coordinator can search for any items she knows will be affected. She searches for data across any of the disciplines whose systems are connected to the platform. Wheels for mechanical, controller for electronic, and so on. She adds these to the affected items alongside the requirements added earlier by the product manager. But what else could this change affect? For that, she'll run the impact analysis. As we saw earlier, this graphical analysis lets us navigate from the highest level item, here it's the master change, to the related items across the system, starting with the affected items that our 2 team members just added. Not only do we see these items, we see their related elements all across the system. As we begin to drill down throughout the system, we can see parent parts, which are blue, along with system elements, which are gray. And because elements from the systems model connect software, hardware, and electronic parts, we actually find a common parent in the system model that relates the wheel to a controller board that drives it and has a piece of firmware on board. Using this built-in impact analysis, the change coordinator determines that the controller board firmware will be affected by changing the wheel thickness, and she goes ahead and adds that firmware to the change. This is a powerful tool for navigating and understanding the impact of the change, which means that the change we just found, the change to the firmware that will be affected by the wheel thickness, would not have been so quick and easy to find without the platform connecting each element in the system across all the different engineering domains and their external data sources, all governed by the systems model. The next step is to create those subchanges, which will be launched into the external software tools as defined by the selections that were made for the affected items. Because we selected mechanical, electrical, and software parts, the subchanges will be driven into those authoring tools, notifying each team of the need for change. With the subchanges launched and in progress, let's go see how they are viewed and implemented in the external tools. First, the mechanical engineer logs in. The 2 changes that relate to this system, which manages mechanical and electrical data, were automatically pushed down from the platform, and you can see them right here. Opening up the first change object shows the affected items related only to the mechanical change. The engineer will connect with the broader team about the change that's needed here. He'll go ahead and add some measurements to demonstrate the old thickness. And a few comments to instruct his team about what needs to happen next. Then he'll add some data that will be pushed back to the platform in the description field for the part, so you can see how the connection back works. The same is true for the engineering change request for the electrical engineering team and the software engineering team. Each receives their change request, views the data associated only with their part, and can push a change back to the platform. Finally, let's see the change made by the mechanical engineering team back here on the platform. The updated description is visible right here on the part. So as the cross-disciplinary team works together on a single master change, their updates are visible to one another here on the Aras platform. The same is true for the electrical engineering team, with all of the electronics data for the rover available right here in the platform, as well as for the software team. You'll notice that the electrical engineer can see both software and electronics information. This visibility into related data across other domains is key to the job that they do. Permissions are set and governed in the platform according to what each user is allowed to see. Because data from each domain is available here on a single platform, manufacturing personnel across different sites and locations can benefit too. Information from every discipline that relates to the product and details about how they relate are combined here into paperless documentation, like the manufacturing instructions you see right now, plus other assets like technical documentation, service specifications, and more. These assets are also kept up to date since they're all stored in context with the cross-disciplinary data and the change processes that govern it across all of the engineering teams, contributing to the product's definition together.